Any questions about this? About the homework?
Number one.
Mind if I take this off? Which one?
First.
Okay. All right, can you give me the specifics?
Sure, I'll just read the thought now. It says, find the resistance per meter of a coaxial transmission line with an inner gold conductor and an outer aluminum conductor.
Inner, all right, gold AU,
Yes.
and so it's solid, and then an outer aluminum
That's right.
AL.
So
All right, and I gave you the conductivities, right?
you gave, let's see.
If you look down there, there's conductivities for the different materials, silver, gold, copper, okay? All right, go ahead.
Yes, you also said there's a frequency of 10 to the 8 hertz. And we also gave the different diameters. A equals 0.5 millimeter, B is 1 millimeter, and C is 3 millimeters.
Millimeter?
Yes.
This problem is kind of a straightforward problem. The only thing you really need is the conductivities of the gold, the conductivities of the aluminum to do it right. And the only radius the two radius you need are the inner and the inner radius of the outer conductor. Everybody follow me on that? Now, when you're doing this, you have to get the skin depths. Let's talk about the one for gold. Gold, the symbol is AU. And for gold, the conductivity, can you tell me what that is? I don't remember it off the top of my head.
Let's see, 2.4.
Anybody?
4.1 times 10 to the 7.
4.1 times 10 to the 7. And the units of this are Siemens per meter, 1 over ohm meters. That's for gold. So the skin depth of gold will be the square root, or 1 over the square root, pardon me, of pi f mu sigma. And, well, you can do this for me. It's mu relative for gold is just 1, so it's mu naught. So this is equal to, can you give that to me? It's 1 over the square root of pi times 10 to the 8th times 4 pi times 10 to the minus 7th times 4.1 times 10 to the 7th.
It's close to 8 times 10 to the minus 6.
8 times 10 to the minus 6, or really 8 microns, right? So that's the skin depth for gold. And for AL, the conductivity is at 3.5 times 10 to the 7th times 10 to the 7th, and the units are 1 over ohm meters or Siemens per meter. So therefore, the skin depth of this is 1 over the square root of pi f mu 0 sigma. You've got sigma there. You can give me that one. Do y'all agree with this? We're just getting skin depths, right? So
9.
not much difference. 9 micrometers. Now we know resistance, AC resistance, is going to have 2 parts. It's the resistance per meter of the gold, or AU, plus the resistance per meter of AL, the aluminum, right? I'm just putting down what's obvious. Here, wait a minute.
Mhm.
All right, here, we can say that RAC, and the reason it is current goes down one of these conductors, say the inner, and it returns on the outer. So the net resistance per meter is going to be the sum of the two. They're not in parallel. So here, when I look at this, the AC resistance is the length. Since it's per meter, the length is 1. And it's over sigma. Well, this is going to be for gold, and that's 4.1 times 10 to the 7th. And then it's times the surface area. And remember, this one I didn't talk about it here, but the skin depth is microns, and the radius, the radius of this thing is millimeters, right? So it's much less. We just use an approximation. And we say the area is going to be 2 pi A, and A is the radius of the inner one. This would be for the gold. It's a half a millimeter, or really times 5 times 10 to the minus 4th meters, right? 2 pi A times the skin depth, and the skin depth for gold was 8 microns, or times 8 times 10 to the minus 6. And when you do that, you're going to get the AC resistance of the gold. I'm going to leave it right there. Plus, and then it's going to be 1 over conductivity for the aluminum is 3.5 times 10 to the 7th times the area, which is 2 pi, times the outer radius, which is 1 millimeter, 10 to the minus 3rd. And then it's times the skin depth, which is 9 times 10 to the minus 6. So if you want to, you can give me the value for each of these separately, so you can have that. What is this one? Let's see. Oh man, is that right? Yeah. Okay, so what do you get for this?
I got 0.97.
For the first part? Anybody confirm that?
That's about what I got too.
9.7 plus, what about the second part?
0.51.
0.51. So when all is said and done, what do you get it for a total? Just over an ohm? What is it? It's 1.4 ohms, roughly? 1.41, something like that. 48 ohms per meter. And what's the answer? Was it
I
there?
think you had 1.5.
All right, 1.5. That's close enough for me. Any other questions? It's a straightforward problem. There's nothing tricky here. All right, anything else in the homework? It's pretty straightforward. There's nothing tricky here. Then I asked for problems with reflection coefficient, standing wave ratio stuff.
Yeah, 6.27 in part B. You might just be able to answer this without writing it aloud, but you asked for the instantaneous magnetic field.
Yeah.
And the equation that you use has beta over the intrinsic impedance instead of 1 over the intrinsic impedance. So I was wondering why.
Maybe it's wrong. Let's take a look at this. So give me the problem. Set me up. Sorry.
The frequency is 600 megahertz.
Okay.
It's a planar wave propagating in the z direction. It's going to hit a material of Teflon with.
It's what?
It's going to hit a material of Teflon.
It's going to strike the material of Teflon. So then we got Teflon. Go ahead.
Relative permittivity.
Permittivity?
Yeah, 2.1.
Okay.
Permeability is 1.
All right.
And the E field is 1 volt per meter in the Y direction.
In the Teflon or striking?
I just have that the E field is 1 volt per meter AY.
In the Teflon then. It's assumed in the Teflon, guys? Is that?
Which number is that?
6.27.
So it's really not striking this. There's no reflection there. Is that? Is it say it's an incident E field that strikes the Teflon in one?
Uniform plane wave incident in Z direction in slab of Teflon impacts.
Okay, that's out here is the field. Yeah. All right, so that means the E field's in a Y direction. And it's 1 volt per meter?
Yes.
Okay, and go ahead, what else did they say?
And then it asks for the E field with Z and T.
Inside the Teflon.
Right.
All right. So the thing about this is we need the reflection transmission coefficient right here, that at the boundary. And you know, unless there's a good reason for not doing it, you always let the boundary be at Z equals 0. Now, normally you have EY up here. I mean, sorry, EX up here. I put EY. Why did I do that? Well, because X is going to go into the board. I did that because so you could see that. Otherwise, I'd have to put a dot coming out to indicate the field. Y'all with me? When I look at this, I need the reflection coefficient. So that means I need the intrinsic impedance of both regions. If we assume this is air or free space, A to naught here, or A to 1, would be 120 pi ohms per meter, right?
Actually, is it on the problem that says electric field intensity is at the surface? Does that change the problem?
Incident on the surface?
Incident on.
That means it's striking it at that, with
It's
that.
not inside. It's just-
No, it's right on the, it's right outside, it's striking it with that value. Incident always means striking, it hits and it's parallel. All right, that's the, here I need the intrinsic impedance of the Teflon. And for that, it's the square root of, well, usually it's J omega mu over sigma plus J omega epsilon, but because sigma is assumed 0 unless specified, and it is 0 for Teflon, the J omegas cancel and I get the square root of mu over epsilon, right? And then I really get the square root of mu naught over epsilon naught times the square root of mu relative over epsilon relative. There's nothing tricky here, right? Well, the square root of mu naught epsilon naught is 120 pi, right? Or 8 to naught. And then the square root of mu relative epsilon relative is 2.1. So this is divided by the square root of 2.1. Correct, class? And I'm just leaving it like that. Now, if I look, since they want it inside, I need the transmission coefficient. We're going to get both. Reflection coefficient is the impedance. I'll put the general form, A to 2 minus A to 1 over A to 2 plus A to 1. Here, A to 2 is the Teflon. That's the media we're going into. And A to 1 is the media we're coming from, which is air. So I can put A to Teflon, or I could really just put A to naught over 1 over square root of 2.1, right? Minus A to 1, which is A to naught, over A to naught over the square root of 2.1, plus A to naught. Now, the reason I left the A to naught there is because I know they're going to cancel on top of the bottom. That way I don't have to worry about it. You all follow me? And then I know the transmission coefficient. We'll calculate that in a second. Transmission coefficient is going to be 2 A to 2 over A to 1 plus A to 2, or it's equal to simply 1 plus the reflection coefficient for normal incidence. This will not be true for oblique. And that's going to be equal to, well, 2 times A to 2, 4 times A to naught over the square root of 2.1 over A to naught over the square root of 2.1 plus A to naught. Y'all follow me what I've done here? Right? Now, if you look at that, the A to naughts cancel, obviously. We really need the transmission coefficient, not reflection, because they want the field inside the Teflon, right? So what do you see this becoming? A to naughts cancel. And I have 2 over the square root of 2.1 all over, and here, you can just do it this way, 1 over the square root of 2.1 plus 1. And you can give me the value for that. Square root of 2.1, 1 plus square root of 2. I can't do that, Mike. Can anybody tell me? You can multiply top and bottom by the square root of 2.1, and you're going to get 2 over 1 plus square root of 2.1. And what do you get for that?
We got like 0.58.
0.58. Is that right? Is that right, guys?
I'm getting 2 over the square root of 2.1, 0.8.
2 over this 1 plus the square root of 2.1.
Yeah.
22. You got 0.82.
Yeah, 0.82. So I'm getting.
22.
0.82?
Yep.
Okay. Now, if you got the transmission coefficient, that means the E field in the Teflon, I'll just call it TE, this is going to be the transmitted E field, this transmission coefficient times incident E field. And the incident E field is 1 volt per meter, so it's transmission coefficient, so it's 0.82 volts per meter would be the magnitude of the E field in the Teflon. Do you all agree with that? All right. Now you want the H field in the Teflon, right? How do we get the H field? What do we need to do? Well, we could write a formal equation, but the real thing we need is what? This, right? Eta naught in the Teflon. So when we look at the H field in the Teflon, its magnitude, if we're just talking about magnitude, most of the times that's the only thing you care about, is going to be the E field in the Teflon divided by eta in the Teflon. So it's really going to be this, or 0.82 over, and this is going to be 125 over the square root of 2.1. And that I can't tell you, but that will be the correct magnitude of the E field. Y'all agree with that? What do you get for this?
Um, 0.0031.
That's what I got.
And that would be amps per meter in magnitude. What was asked for?
The other one is power.
In the Teflon?
In the Teflon, yes.
All right, the Teflon has no loss, right? So the intrinsic impedance is strict real. Do you all agree with that? And we know if we want the average power, PAV, technically it's 1/2. Don't write this down, just listen to me. The real part of E cross H conjugated. I mean, if we wanted to be formal, we could introduce a coordinate system and do all that. We don't need to do that. It's losses. That means it's going to be 1/2 magnitude of the E field in the Teflon squared, I better call it, in the Teflon. So the magnitude of that squared over the intrinsic impedance in the Teflon, which is 120 pi over the square root of 2.1, right? Well, the E field in the Teflon is that. This is one way to get it. You follow me on this, class? You can just take the E field and square it, because if you take 1/2 real part of E cross H, H is E over eta, right? So you're going to get an E naught squared no matter what you do, right, class?
Mm-hmm.
And Just tell me what that is. This E field right there on the Teflon is 0.82. So you take that 0.82 squared, divide it by 2, then divide it by 120 pi, and multiply it by square root of 2.1. What do you get for that? I think I provided you with this answer, but I'm not sure.
At 1.9 milliwatts per meter squared.
Is that what you got, guys?
Yeah, still working it out.
1.9
Milliwatts per meter squared.
times 10 to the minus third watts per meter squared. And what was your question about the beta thing? I was trying to figure out where.
When I did the problem, I originally thought that you only had to use eta naught. So I was confused as to why you had the square root of 2.1 there.
Okay. All right. Out of curiosity, what would beta be out here? What would be beta 0 in free space? How would you get beta? There's a lot of ways.
Could solve the propagation.
Well, we know it's going to have alpha 0, right? Beta, because of that, would just be omega times square root of mu 0 epsilon 0, since mu relative and epsilon relative are 1. And that's really just omega over the velocity of light, isn't it? Because the square root of mu epsilon is 1 over c, or c is 1 over the square root of mu naught epsilon naught. Well, that means it's simply 2 pi times f over 3 times 10 to the 8th. This is a nice thing to remember for losses. The frequency is 600 megahertz, or 0.6 times 10 to the 8th, over 3 times 10 to the 8th is 0.6 times 2 pi over 3. And you can see what beta is then. It's going to be small, right? You could also find beta in here. What would you do differently? It's only a slight difference. I would have square root of mu naught epsilon naught, then times square root of epsilon relative, right? Y'all with me, class? Because mu and epsilon here, I just put mu naught epsilon naught because it's free space. Okay. All right. Other questions?
Let's see. Problem 630. It's I had a question on the equation, but I mean, if you wouldn't do it out, sum it up.
Sure. Okay.
Yeah, I'll go ahead and read that. It says a 200 megahertz uniform plane wave incident on a thick copper slab imparts a 1 millivolt per meter amplitude of the surface. How much power passes through a square meter of the surface?
All right. Help me out here. Say that again. The E field out here?
I'll just read it. It says a 200 megahertz uniform plane wave incident on a thick copper slab imparts a 1 millivolt per meter amplitude at the surface. How much power passes through a square meter at the surface?
All right. If they're saying, what was the E field again?
It just said the magnitude, which is 1 millivolt per meter.
All right. Here's the problem with this. If it's 1 millivolt per meter on this side, striking it, much less is going to get in. If you assume it's inside, now I would state clearly on any exam or quiz that the field was either out here or inside. All right, you with me on that? Here, I'm going to assume it's inside. This is a Whitworth problem. All right, if it's inside, then this is important to follow. I need to get first the intrinsic impedance in copper. So the intrinsic impedance for copper it's a good conductor. Do you all agree with that?
Mhm.
Sigma for copper is about, it depends what book you're looking at, 5.8 times 10 to the 7th ohms, or 1/ohm meter, pardon me, 1/ohm meter. Now, you'll see 5.7 times 10 to the 7th. What it amounts to is the type of copper and if the impurity level. And copper, like most metals, they ally, and it's how pure it is. I never heard of polycrystalline copper, but it might exist. So it's 5.8 times 10 to the 7th, I believe. Is that what the book has? What we're supposed to?
Is 5.96 times 10 is close.
5.96 is that? Wow,
Conductivity.
Huh?
5.96.
that's high. All right, that's a very high value. If you look on Google conductivity of copper, if anybody can, just take a look. You'll get values that are different. I think it'll be 5.8, 5.7. And it depends against,
I've got 5.8 on the back of this in Appendix E.
5.8?
For copper.
Yeah, that's
That's
typical.
exactly what I'm-
What did you get on Google?
It was, 5, yeah.
5.8?
Yeah, 5.7, something like that.
5.9 is a little bit high, but again, if you got super pure copper, it's feasible. Problem is, that doesn't exist usually. I mean, it exists, but it probably costs a fortune. I'm not an expert in that. Anyway, did they use 5.96 in the problem?
Okay.
Let's use 5.8 because it's easier.
Yeah.
So when we do this, and now we could go ahead and get a mega epsilon, but I'm going to make the case that the copper conductivity is much greater than a mega epsilon. You can go ahead and prove that if you want, but it's much greater. So I don't even worry about it. And because of that, I say the conductivity or the intrinsic impedance is just equal to J omega mu over sigma. I'm not even going to bother putting the J omega epsilon. So that's equal to really the square root of 2 pi f times mu 0, mu relative is 1, over 5.8 times 10 to the 7th, right? And that's the square root of that, and f is 200 megahertz, so it's going to be at an angle of 45 degrees. I didn't even put that down. Or pi over 4. What do you get for this? Square root of 2 pi f mu 0 over 5.8 times 10 to the 7.
Like 0.005.
All right, 0.005. Anybody second that?
Yeah.
At an angle of 45 degrees or pi over 4, right?
Yes.
Now, we're going to assume that that E field is the electric field in the material, in the copper, to see how if Whitworth meant that, then we'll use it. If not, we can figure it out in a second. So that's the electric field inside, and that means the average power from last time is equal to 1/2, right?
Mhm.
Now, technically, it's the real part of E crossed H conjugated, but we know if we have a conductor or any material that's propagating plane wave, it's going to be 1/2 magnitude of the incident field squared divided by magnitude of eta naught, or the intrinsic impedance, I should say, magnitude of the intrinsic impedance times cosine of the angle of the intrinsic impedance. In this case, it's going to be 45 degrees. And then it would be e to the minus 2 alpha z if it's propagating in the z direction. There you see. We don't need to concern ourselves with that, do we? They just wanted the power density at the surface, right? And the power densities units are watts per meter squared. So if you look at this, we have 1/2 magnitude of the E field is 1 millivolts, so it's 10 to the minus 3 squared divided by 8 or not, 0.005. And then the angle here is cosine of 45, right? And the cosine of 45 degrees is 1 over the square root of 2. What do you get for that value? See if it's consistent with Wimper's. Dr. Wood. Let me tell you something that's small. That's 10 to the minus 6 over 5 times 10 to the minus 3rd, 10 to the minus 4th over square root of 2. So what do you got about what? Of the order of 10 to the minus 5th, 10 to the minus 6.
Yeah, so like I got 7 times 10 to the negative 5.
Anybody else?
That's what I got.
And that's watts per meter squared. What did Whitworth have? Dr. Rowe?
9.6 times 10 to the minus 5. That's
We also used the other copper. So.
No, that ain't gonna make that big of a, that means he assumed that electric field's on the other side. If this electric field was inside, this is 7.5 times, or 7 times 10 to the minus 5th. Whitworth's answer was what again?
9.6
Times 10 to the,
minus 5.
no, that's too close. Is that,
I'll punch in the.
I'm gonna suggest one.
5 point.
Is this the right answer for that? That's a 200 megahertz?
Doesn't look like you multiplied it by cosine.
He had to have, or he would have, oh yeah, I take his answer, multiply by the cosine, he probably forgot. You have to have that cosine in there,
0.0.
because it's cosine of 45. Is that gonna give you, or not? It's 1 over the square.
Gives you 1 to the negative 4,
What?
or 1 times 10 to the 4, negative 4. So it's close. It's
I'm gonna
Yeah,
bet
fine.
2 things. One is he used 5.96 times 10 to the 8th for the conductivity, and 2, he didn't multiply it by the cosine. But that would account for it, I think. All right,
Pretty close.
y'all with me on that one?
Mhm.
Any other questions in that one?
That's right.
Now, if that E field was outside here, then you would need the transmission coefficient, right? You have to multiply the transmission coefficient times the incident E field to get the E field inside there. And then you'd have to take the power equation. Y'all with me? All right, anything else? Good, I'm glad you guys are doing this stuff. Okay, today. We got any rain in the forecast, anybody? I'm hopeful. My yard is gonna start drying out.
Yes.
I don't know if we have rain or not, guys.
Doesn't look like it.
Nope, not at all. The whole week.
I tell you, I've been down here when it didn't rain for almost a month, I think.
Yeah.
And the reservoirs get real low and they have sprinkling vents. You guys go out to the lakes that are around here or not?
Occasion.
If you go to Lake Martin, West Point, any of that stuff, you're gonna find out that all of a sudden, when you start seeing the end of the boat ramps, you gotta put your boat down in the mud. Things start getting a little concerning if you have two-wheel drive. All right. So the next thing we're gonna talk about, there's about 3 or 4 things I can talk about in any order because they're seemingly unrelated. But the next thing I'm gonna talk about is something called polarization. Now, I don't spend much time on this. And this, I'm gonna find out where it is. You find it before me on polarization. Page 347. I'm going to try to explain this in a way that it makes the most logical sense. All right, first, let me give you this discussion. So we talk about electric fields. Unlike sonic waves that are in the air, a sonic wave has compression and rarefaction, so it expands and contracts. An electric field has something, an electric field vector, and therefore the force on a charge is perpendicular to the direction it propagates. Think about a string. If you take a string and give it a crack, then a wave propagates, but the displacement of the string is perpendicular to the direction the wave is going. You all follow? All right. Well, with an electric field, because it has a directional sense, if it's propagating in that direction, the electric field, if it's a plane wave or if it's a propagating one, the electric field and the magnetic field have to be perpendicular to the direction of propagation. Now, if we think about an antenna, the direction of current will always have or give you the component of the electric field. So if you have a vertically polarized electric field, vertically polarized current, if you have a straight wire antenna where the current is moving up and down, it'll launch an electric field like that. As you're moving up, the magnitude of the electric field goes down at a given radial distance. And when you're directly above it, it's zero. We'll see that in chapter 8. All right? But nothing is propagating right above it. All right? So the electric field is oriented this way. If the antenna was this way, horizontal, this would be the direction of the electric field. The direction that the electric field from an antenna points gives you what's called a polarization. Now, if it only has a polarization in one direction, so that the electric field grows and contracts in just the vertical direction, that's called linear polarization. Don't worry about the names. Just follow me. You all follow me? It should make logical sense. It's linear. It goes up, it comes down. It goes up and comes down. But there's another thing that can happen. I can have an antenna that has currents in the horizontal and vertical directions. Y'all follow? This would be a quadrupole antenna, something like this, where I have fields going this way and this way at the same frequency. Now, this would cause one in this direction. This would cause an electric field in this direction. If they were exactly in phase, then you would have something that would have a diagonal linear polarization. They would both add, go to a maximum, then go to zero at the same time, and vice versa. Do y'all follow me on that? Here's something unique. If these have the same magnitude of electric field generated, but they're 90 degrees out of phase, then as one is becoming a peak, the other is becoming a minimum. And when that happens, you get circular polarization. And if you were to look, if this field was coming through the board, and we could look at the projection of the field only on the board, and it's coming this way, you would get something like this, and this is called circular polarization. You would have this. You would have a constant amplitude, E naught, but then the electric field would move this way. I'm going to show you something, but it would create a circle, right? And it would always have that same amplitude, constant amplitude, but as it's propagating, it would do this. I mean, you can think about it like going like this if you froze time. You all follow me? Corkscrew. Electric field has constant magnitude, but the orientation changes with time and space. That's called circular polarization. If you take your right hand, I'm not really worried about this stuff. This is all just kind of, it's classification. If you take your right hand and you take your finger and put it in the direction of the electric field, if it's rotating like you're closing a door or like this way, that's called right-hand circular polarization. And if it's going in the other direction, it's called left-hand circular polarization. Boom. The bomb. Okay, good. Now we solved that problem. So that's circular polarization. Now, if the magnitude of the currents is different in the end, or tangent links are different or both, then you can get something that's neither circular nor linear. That's called elliptical. And you get an ellipse. Do y'all follow me on this? Now, in general, there's a lot of ways to mathematically describe this. Elliptical polarization can look like this, right? And there'll be something that they call a tilt angle, which is the tilt angle. All right. This becomes important with weather radar, and I'll explain. And if the tilt angle is 0, then it's straight up, and you got a long axis or a major axis and a minor axis. Now, if the two waveforms become in phase, then it just straight line at that angle. And they can, I'll just tell you this much. Mathematically, there's so many ways to describe this, I don't even worry about it. But here's why it's kind of important. There's 2 or 3 things. So when you have any kind of system, specifically radar, that you're interrogating a region with, if you send out a right-hand circular polarized wave, when it strikes a conducting object like an airplane, it will reflect back a left-hand circular polarized wave. Right? Why is that important? If I know I sent out a right-hand circular polarized wave, I can develop a filter that gets rid of everything except left-hand circularly polarized wave returns. And therefore, I can discriminate on what's out there much better. The only thing I care about when I've got a radar is what's reflecting back to me that I sent. I don't care about some guy with a jammer out there. I don't care about a radio station that happens to have a harmonic in that frequency range. I care about what I send out and if it has the right polarization. Send it out right, it comes back left. It's likely my signal. I take a look at the time delay and I can get the range because I know it's moving the speed of light. I teach radar, like radar a lot, and I like EMC a lot, and all this goes to both of them. Now, why elliptical polarization? Why would you want elliptical polarization? Well, a lot of this has to do with weather radar. Because when you have polarization, what you can do, if you have an elliptical polarized wave, you know that raindrops, as they come down, a raindrop will have kind of a teardrop shape. It'll have a long major axis and a thin minor axis. Well, with elliptical polarization, you can maximize your backscatter, assuming the thing's falling directly down. Now, there's other things. If you're looking at something where you want to see the actual angle that the rain was falling, and I have not done this, I'm just speculating, then what you could do is move that elliptically polarized radar this way, like so now the tilt angle is changing, and when you get a maximum power return from that event, that's likely going to be the tilt angle that the rain's coming in with, and you could, or I should say, it's graupel and ice a lot of times, but the stuff is moving at. So they can actually identify the actual rain field, direction of the rain field. Now, there's a lot more to this, but generally speaking, when you talk about circularly polarized waves, they're right-hand circularly or left-hand circularly polarized. And with radar, sometimes they'll jump between the two, because if there's a bad guy out there and he wants to jam you or something, then he has a harder time figuring out what you're doing. You're sending out right for a second and left, and there is no rhyme or reason to when you're sending what. But I know when I send out a right, I start listening for a left for a specific length of time, and vice versa. And that's why polarization becomes really important. Now, there's other, when they do geoscience work and they look beneath the earth with radar, there's ground penetrating radar, then they can find actually things that are Well, they can have, it's easier to differentiate materials by the amount of reflection that's right versus left-hand polarization. Just realize that's the real reason, because the more conducting a region is, the more the actual reflections will be right hand. And that's about, honestly, as far as I go with this. Just, it's really a good conductor. Whatever you send out, hit it with, it comes back the opposite polarization. Now that's sort of the bread and butter of radar, using polarization. Okay. Now, a good thing you should be thinking is, what would I ask on a quiz? About polarization, if it was right or left hand. How would you figure it out? Plot 2 or 3 points in time. Let me just give you an example. Because I know I'm going to give you some problems, but level with you. Polarization is not something I worry about in EMAG 2. Just don't. If I'm teaching something about geoscience or radar for, I guess, weather storm event classifications, I would. If I was teaching something with, have you heard of a hook echo with Doppler? Ever? Have you heard of Doppler radar? That's velocity. They can the velocity of particles and the thing. But when they're doing wind shear and stuff like this, and then wind field, then I'd probably spend a lot more time with polarization and methods of cataloging it and discriminating events. But so let me just show you what could be asked. Suppose I had the total E field, and we're going to assume it's Z equals 0, so I won't even bother putting all the cosine of omega t minus beta z, is equal to some E naught, and I'm going to put cosine, in fact, let me make this exact. I'm going to put 2 cosine of omega t here, AX, plus 3 cosine of omega t plus pi over 4, all right, AY. And I'm going to say it's probably, this is at Z equals 0, so we don't have to worry about the beta z minus beta z business, okay? So what kind of polarization is that? Good question. Here's how we do it. We plot a few points. Call this the x-axis, call this the y. We know it's propagating in the z direction, right? Start at omega t equals 0. All right? So that means the cosine of 0 is something I need. What's the cosine of 0? 1. So on the real axis, it would be out 2 units, right? Now what about, the horizontal. What about the y-axis? I have omega t 0, but I have pi over 4, 45 degrees, right? What's the cosine of 45 degrees? 1 over square root of 2, right? So if I have 3 over square root of 2, can somebody just tell me what that is? That would be how far up I got to go.
2.1.
Say again?
2.1.
2.12. So it's 2 this way. It's just a little bit more than it this way, right? So that's the first point, right? That's the first plot. Strict. All right. Now let omega t be equal to pi over 4. I move it 45 degrees, all right? All right, the x1 is going to be 2 over the square root of 2, right? Because I have 2 times cosine of 45 is 1 over square root of 2. So that's going to be 2 over square root of 2 or square root of 2, which is 1.414. So my second point is out here somewhere. Start tossing those. I wonder if this works. Is this? Oh, that's kind of cool. I hope that erases that. Yeah. So the next point is here at 1.414, right? Square root of 2. And what about the y-axis? Now I have what? Well, I got pi over 4 plus pi over 4 is cosine of pi over 2. Cosine of 90 is 0. That means it's 0, correct? So that was the first point. The second point is here. 1, this is 2. Can you almost see what's happening? Where do you want to guess where the third point is? If I go for omega t, we'll do it. Omega t is pi over 2. All right, now just look at this. When omega t is pi over 2, what's x? Oh, I mean, what's the x component? Cosine of pi over 2 is cosine of 90 is 0, right? So it's got no x component. What's the y component? Well, it's the cosine of what? 3/4 pi or 135. Cosine of 135 is minus 1 over square root 2, isn't it? Yeah, it's down here. Can you all see what's happening? This thing is going to be a left-hand elliptically polarized wave, and it's going to be moving this way. Going to come down here, and then you all see what's going on? I don't ask the tilt angle. I could show you how to do it. But it really, I mean, that's how you find out if it's left or right. If it was circular, the actual length would never change, right? Here, it's obviously changing. You all agree with that?
Mm-hmm.
That's it in a nutshell. That's the if I was going to ask anything, go ahead.
So clockwise is left-handed. And
Yeah, well, take your right hand. Everybody's got one of them, and you don't. All right. Put your thumb in the direction it's propagating. Out of the board in a Z, right? If the thing's spinning this way, or I say as if I'm opening a door upside down, right? That's right-hand polarization, clockwise. I mean counterclockwise. Take your left hand. If it's going, take the E field and it's moving this way in time, then it's left-hand polarization, circular polarization. There's no mystery to this stuff. Just have a left and a right hand and you should be good.
Okay.
But there are people that are amputees, so I gotta be kind of careful. Everybody has a right hand. I'm not trying to be funny, I'm being honest with you. There really are. And I had a lady who was nearly deaf, and she made me wear a mic. She recorded me, and I had to look and talk slowly. And then have you ever seen a blind student? There are students that are considered legally blind, and they get everything in Braille. They are amazing. I don't know how, just feeling that you can get it, but they have they have basically a lot of raised dots and stuff that are the letters, and they can read and everything. It's amazing. Okay. I think what else? I wish I had something more profound to tell you about the polarization, but that's it. When we get into antennas, maybe I'll talk about how to make some of these things, polarization filters and stuff like this. Probably a lot of stuff I don't know. All right, we talked about loss tension. The next thing we're going to do, now this isn't really in Wentworth's book, but I do it, and that is talk about something that's used everywhere. It's called shielding. You've probably heard the term shielding. And this is going to be shielding with a layer of good conductors. Now, I teach electromagnetic compatibility, and I'll tell you one thing, that there's so much in that course that's so useful that a lot of design engineers probably don't know. But it's super useful. And the people that, what's this saying? Bring good things to life are the ones that are highest paid. By that I mean, you can have any kind of design you want. If you're at Adtran or Dynetics or whatever, you can come up with the greatest chip designs and all that. When you go out to implement them in cell towers and stuff, all of a sudden the grim reality happens that, hey, these things they're susceptible to lightning, moisture, what have you. Probably the highest paid engineers are called compliance engineers. My friend's father, I went to school with this guy, he was at Penn State at the same time. His name is Jaffe. He works for Adtran up in Huntsville, Alabama. And he makes a fortune because he's a compliance engineer. The head guy up there is Kevin Schneider. He's another compliance engineer. He's the chief technical officer. These guys figure out electromagnetically or thermally or whatever, what's wrong, and make it right so the thing passes FCC specs. FCC is the Federal Communication Commission, and they specify the limits of how much something can radiate. And also, they have to figure out what's, if lightning, when it strikes the tower, if it's causing your system to fail, or then you've got to find a way to make sure it doesn't. And that's where he comes in, because he's paid a whole lot of money. So he troubleshoots at the end product. Just before it gets out the door, he's the thing that makes it comply or work in the real world. And believe me, most stuff, even my car is a 2010 Veracruz. And just about a week ago, actually a week ago Monday, I got this notification that my alternator may go out because of they found this flaw in the oil gaskets, oil coverings on my car. I think it's 2010. You tell me it now. It's a little. He said, but we have a fix for it. Basically, take it in. Well, unfortunately, about 4 or 5 months ago, my alternator went out, and I was dead in the water. This can kill you, by the way. If you're driving down the highway, you don't know you have a bad alternator, and your battery goes out, right? Because it doesn't charge. An alternator charges the battery. That car is all electric. Basically, everything goes into a failure mode, and you crash. Well, luckily, I was at a red light. I mean, I was coasting towards a red light, and my car just died. I couldn't take it out and drive. As a matter of fact, this is one of the weirdest things I ever had, because almost any car I've ever driven, I think any car, allows me to put it in neutral or put it in drive whenever I want. This one didn't. It's all electrical, and it could kill you. So well, it's nice to know. Tell me now. But I've already had the alternator replaced and fixed the leak. So now I'm in the process of getting a refund of $960 from Hyundai. However, the moral of the story is the guy that found that should have done it at the front end. They should have discovered the failure, because now it's going to cost them in lawsuits and everything like that. There'll be tons of lawsuits. If somebody was in an accident, seriously hurt, or hurt somebody because of that failure, Hyundai Motor Company is going to have to pay. Now, I don't think motor companies have separate insurance. Usually they insure themselves, so they're going to pay one heck of a price. And I could claim I had, irreversible psychological problems, but I'm not a liar. But I could see somebody doing that. I'm not lying. All right, now back, and one of the things the compliance engineers do, EMC people that I teach, is use shielding to prevent problems that lead to crashes. So this is shielding. A Monday story time, right? So here's what shielding boils down to. I'm going to have some thick piece of metal. I'm calling it thick. A millimeter, that's not thick, but it's thick for what I'm talking about. And this is going to be a shield thickness. And it has some conductivity, and I'll call it sigma SH, and some permeability, mu relative. Almost always epsilon relative is 1, but it can change. Anyway, the shield has a large conductivity. It's going to be a good conductor. Y'all follow? So you can assume for shielding that the sigma of the shield is much, much greater than omega epsilon. Just don't worry about epsilon omega. Now, when you have an electric field incident on a shield, and it's coming this way and it strikes, what you need is to figure out what the impedance is looking this way. You want to find out what the intrinsic impedance is looking in that way. Now, here's where I draw to something, I draw an analogy to something you've already had. Remember when you had this? You're going to see this gets easy. You remember when you had a transmission line with a characteristic impedance Z0, and then you had a load with ZL on it, right? Mm-hmm. You found out one thing. If this is link L, you said that Zn was equal to Z0, the characteristic impedance, times ZL plus, and you put it J times Z0 times the tangent of beta L if it was lossless over ZL plus J Z naught, excuse me, Z naught plus J ZL times the tangent of beta L. Do you remember that? All right, that's for a lossless region. For a, quote, lossy transmission line, it would be Z naught, and you don't have to write this down, over ZL plus, there would be no J, and it would be Z naught times the hyperbolic tangent of beta L over Z naught plus, and then ZL hyperbolic tangent of beta L. And it wouldn't even be beta L, it would actually be gamma L. And gamma would be equal to alpha plus J beta. And for a transmission line, if you remember anything about that, that was R prime plus J omega L prime times G prime plus J omega C prime. And you don't have to know that, but that's the formula for R and L prime and G prime and C prime are the resistance, inductance, conductance and capacitance per meter. Y'all remember that? All right, you don't have to worry about that. But what I need to do is draw a parallel between this guy right here and this guy here. Now you can see that this is this guy right here is lossless, this is lossy. It doesn't have the J and it's got a hyperbolic tangent. When we talk about the input intrinsic impedance here, we can say A to N. Now, in Whitworth's book, he may have this wrong in yours, is equal to some eta, and you see where it's Z naught here? Well, that Z naught has to do with the environment the wave's propagating in, right? Not the load. Here, this is like Z naught, and that would be eta of the shield, right? By the way, I didn't put it down there, but eta of the shield would be equal to the square root of J omega mu over sigma. You can just say it's about that, and you can forget the J omega epsilon. With me, guys?
Mm-hmm.
Now, with that in mind, this eta of the shield, eta in here, is going to be eta of the shield times eta naught. Now, here's what's happening. We're saying this region is like Z naught, and we're saying this region is like ZL. Right, the load is like free space on the other side of the shield, and the shield is like the transmission line. That's the thing it's propagating through, right? So it's lost. Anyway, you're going to have eta naught here, which is free space. Call it air. Call this air. And there's not a plus J, it's going to be plus, and then it would be eta of the shield times the hyperbolic tangent of gamma times L over eta of the shield plus eta naught times the hyperbolic tangent of gamma L. Now you'll notice this parallels this entirely because eta naught here will be lossy, right? And eta L is really going to be free space. Can you all follow me on that? I think Whitworth's book has this as a plus J, and that's wrong. This is the one it should be. In EMC, you would see how we do it, but this is what it comes down to. Now that's the input impedance. However, if the skin depth is several times L, what actually happens is this. Wave comes in here, a little bit gets in, it comes, hits this surface, reflects back, reflects. Did you have multi-bounces in transmission lines? Remember the bounce diagrams, anybody? Well, you would learn that the wave coming in here is going to come down, it's going to hit this and ricochet back, hit here, and every time it goes through, it loses a lot of its amplitude because it's conducting. When it hits here, only a fraction is reflected and it comes back this way. Basically, if you have a shield that's more than about a skin depth thick, you really don't worry about multiple reflection, because just think of this. I got down here, I'm attenuating. I hit here, now I get fractions of the amount I struck it with. When it comes back here, it's going, it goes and it decays, then some of it's transmitted, some of it's reflected more. By the time it does its first reflection, it's about nothing. Most of the time. So what we do is this. We can say this is about equal to just n of the shield if the skin depth is greater than the actual thickness of the shield. Almost all shields are several skin depths thick. Y'all follow me? And skin depth is a function of the frequency, the lowest frequency they're going to be used at. Everybody with me on that? Okay. Now, having said that, I'm getting out of time, but I'm not quite there yet. I think I got 5 minutes. This book covers this in a later chapter, but this is the perfect place for it because we just had what the intrinsic impedance was in good conductors. So now we can say that the actual, if I take an electric field here, that's the incident electric field, and let's assume I know eta shield. Now there's two things I have to concern myself with. First, I need the transmission coefficient right here. Call this boundary 1 and this boundary 2. So I need the transmission coefficient there. I don't have to, but I can get the transmission or the reflection coefficient there. You with me on that? Now, as that wave comes in, then it starts decaying, and I'm going to take you through it. So my goal is to find what the electric field is transmitted. All right, I'm trying to figure this out. So I can say the transmitted electric field would be equal to, start with the incident electric field. Then it's times the transmission coefficient right here, and I'm going to show you what that is in a second. Then that electric field is going to start decaying at e to the minus alpha z. So something I can put down here is propagation constant in the shield is equal to the square root of j omega mu. Usually it's sigma plus j omega epsilon, but here I just put sigma. So that means gamma of the shield is equal to alpha plus j beta is equal to 1 plus j times the square root of pi f mu sigma, which is 1 over the skin depth. You remember that? And alpha is equal to beta. Do you all remember? If you don't worry. Just take a look at this. This is, because remember, normally it's sigma plus j omega epsilon. The j omega epsilon is gone because sigma dominates. Okay. Now, really the 1 plus j, remember I can take square root of j and say it's 1 plus j with square root of 2. Factor in the 2, and omega's 2 pi, 2's cancel, I'm up with pi. So, here I say the transmission coefficient in region 1 is 2 times eta shield over eta shield plus eta naught. It's coming from air, so it's eta naught. I'll leave that there. Then it will decay as e to the minus alpha z. Now this is strictly magnitude I'm worried about, not phase. Y'all follow me? That thing is now, as it's propagating through the shield, it's decaying, right? It's because it's got a lossy material there, so it's going to decay. Then it's going to hit this side. And there's going to be a second transmission coefficient. Here's something neat. The first one is this. The second one is 2, it's twice the impedance you're going into, eta naught, over eta naught plus eta shield. Now here's something interesting. This value of eta shield is super small compared to eta naught. Eta naught is 377 ohms about, with me? That's 120 pi. Eta shield almost always is less than an ohm. It's tenths of an ohm. And therefore, when you look at this, I have 2 times eta naught over 8 naught plus almost nothing, it's really just 2 8 naught over 8 naught or 2. And that's the truth. So that second one is about 2. And it makes this equation look like 2 E naught incident times the transmission coefficient, N1, times e to the minus alpha, and then z here would be the thickness of the shield, L. Here, I can just put L here. That, in fact, would be the electric field that leaves the shield. Are you with me, class? Now, there's one last thing. With shields, they typically talk about shielding effectiveness. So when you talk about shielding effectiveness, or SE, that's equal to 20 times the log, that's a log base 10, of the incident electric field divided by the transmitted electric fields. And you better put magnitude here, because some of you may end up having a phase in there. So it's really 20 times, you'll notice how E incident occurs in both. It's really 20 times the log base 10 of, and it's going to, the E naughts will cancel, you get 1 over 2 tau 1 times e to the minus alpha L. And that is about the shielding effectiveness of any kind of reasonable shield. Make sense to everybody? Shielding effectiveness is used because usually the electric field that's transmitted is 10 to the minus 4th, 10 to the minus 5th, 10 to the minus 6th, the value of the incident field. So you get so many orders of magnitude, it makes sense to talk about the logarithmic change, or 20 times the log of that value. Think about this. If this number here is 10 to the 4th, all right? Well, the log of 10 to the 4th is 4. 4 times 20 is 80, right? If it's 10 to the 5th, the log of 10 to the 5th is going to be 5, right? 5 times 2 is going to be 100 dB. And shielding effectivenesses of over 100 dB are probably very reasonable for a lot of shields. Do you need it? Well, maybe not, but it's always nice to over-design things. Usually what they try to do is they want a design that is basically able to take 10 times the worst case thing you can imagine when you're doing with electronics and stuff like this. That way, even if an event happens you haven't thought about, electromagnetic, say lightning or something like that, you're still, even if Mother Nature came up with a whopper that was 10 times the largest ever measured, it's still, your shield that you have would still be okay. Yeah. I'll give you more homework on this, and we'll see you Wednesday. I hope we get some rain. Maybe next week.